thanks for coming. I very much appreciate the opportunity to be here with you all. And I would like to thank the organizers for allowing me to do that. So with that, hello, my name is David Hopkins. I'm retired from NDSU. And so the honorarium, which actually just going to be in minutes. Soil is life on the rocks. I'll talk a little bit about that in just a minute. But today, I'm going to just move along and share with you as best I can. This is sort of a travel log, to be honest with you. It's a travel log of some of the soils of the basins. And I always have to share as much as I can. Oh, this is really that close? This, okay. Yeah, okay. So anyway, okay, well, let's just get going. Okay. So today, geography and properties of soils of the base of lake. So today, okay, there's going to be a couple little advertisements for soils education. Okay, and that'll be part of this. There we go. Okay, so soils with natural bodies, obviously, that's what we're here for. We're here for agriculture and soils and natural bodies. I'm going to talk a tad bit about the major physiographic regions in the basin. Know your geology. That's what that little thing's about. A soil travel log, a sort of a short soil travel log. And then a couple, just a few examples from some work we did with the Devil's Lake test project back in the early 2000s as well. And then finally, a little mini cautionary tale about where we are in agriculture in terms of soil quality in North Dakota today. Okay, in my opinion. This is a quote by Yenny. Okay. It's absolutely true. It's absolutely true on human timescales. Its mass is non-renewable, but its mass changes a lot, as we've seen. So as we move along, here's the first ad. Many of you have taken soils classes. Many of you have grown up on farms. Obviously, soil formation is a factor of climate, living organisms, parent material, and time. We always think about this. And so those are the factors of soil formation. This woman is walking into an ancient soil in Illinois, the great famous Sangamon Paleosalt. Okay, the parent material of that soil is that loess, the Roxana loess above it. There was another layer that's very similar. That was a different layer, and she's walking. That loess is 55,000 years old. Okay, all that buff layer is loess. And that Sangamon soil formed in that loess something like 130,000 years ago to 70,000 years ago, or something like it, during a warm cycle of what we call the interglacial. And so there you can see this phenomenally orange, reddish color of the soil where the arrows are going. And it's the story of transformation. It's just totally the story of transformation. And obviously we gain all of the agricultural values of soil from soil genesis playing out over hundreds and thousands of years in terms of making those soils what they are. And this, I have a slide here, but I had to cut it because I've only got 100. And so I'm just going to let you see this one. The recognition that the soil horizons themselves actually reflect history and can be dated is probably, as Jan Danielon said, the most important discovery in pedology. Okay, this goes back to 1910 and 1890 and 1930. And now we've got all these new chronologic methods to figure out how precisely we can date things with oxygen isotopes and carbon dating. I'll share a little of that with you in a minute. So that's the first ad for soils, is thinking about the factors of soil formation. If we look at the basin, this is a map from the what we call the Northern Tier study that we did. This is a parent material map. So the soils are all based on the actual parent material. So we're not looking at specific series here, although it's based on that. I hope this is a pointer. It's not, it is. It's a pointer. There. Okay, see this infinitesimally small red thing here? Okay, so there's the Souris Lake Plain, the Lax Basin over there. Here we are in Devil's Lake here. There's the Candu Lake Plain. And we've got, that's all referred to as Silty Lake Plain. Over here, of course, the Pembina Escarpment. The sunrise was coming as I was just up by Michigan this morning. There's our shales of the Pembina Escarpment. As you come up and drive out of Grand Forks and head towards Michigan and Niagara Cemetery, you're climbing old rock, and we'll talk about that in just a minute. But the largest area, of course, that you can see, sorry, it's impossible for me to find this pointer, is, of course, the fine loamy till plain. These are our barn soils. These are our butte soils. These are sadly our Langhai soils. They are our Svea soils. There are our Tonka soils. This is the parent material of all of this incredible the breadbasket of North Dakota. And so again, if we look at the legend here, you can see very simplistically some of the decisions that we made when we tried to correlate 1,000 samples to look at zinc and cadmium concentrations in the soils of northern North Dakota. Fine loamy till, as you can see there. Some of this material is very different than others, obviously. Those of you that farm and know the coarse loamy tills know that you're looking at much lower clay contents in your till. There's marvelously productive soils on coarse loamy till, but it doesn't have the same water holding capacity as the fine loamy tills. Another aspect of those particular types of tills is that there's a lot of stratification in the actual material itself. As Cornelius Height used to say, it's more of a landscape than anything else, but there's a lot of lateral water flow issues in the coarse loamy till. So it's an interesting and productive area, but you have to be careful with it. Two sites that we'll take a look at in a little bit are Site 6 and Site 7 from the Devil's Lake Test Project. I'll show you some maps of some of that in just a bit. Again, the advertisement going back to some 60s or 70s, early 70s, NRCS, know your soil. And so one of the things I want to share with you real quickly right now is I started working with John Lukash up in the Devil's Lake, up in the Langley substation, as it used to be called, now it's a wonderful REC. We were looking at characterization data to try to help plan some of this cadmium and zinc work back in the late 90s. And so I was taking a look at at soils like Cresbar, dealing with an Excel spreadsheet that the wonderful Jim Seaholm put together back in the early 90s. And this took hours to put this together. How many of you all in here use the Soil Web app on your phone? Raise your hands. Don't be shy. Get those hands up so I can see them. Come on. Okay. Well, then you guys can just go get the coffee now. But for the rest of you that don't know that app, okay, which is easy and free, you can simply go to this NRCS website and you can put Cresbar in right there. And if you look at the Soil Explorer in the upper green there, right by where it says Cresbar, you can see the distribution of Cresbar in its whole geographic range. Of course, it's not perfect. If you go down to one specific section there, yeah, it might be Cresbar or it might not, but this is the distribution of the Cresbar soil series in our state. It's home, of course, to South Dakota, and that's why it goes down into that. That's where the type location is. The important thing, geez, they make this thing for midgets. The important point here, folks, for you all, these red points down here, several in South Dakota, some up over here in the Des Lacs, a couple here closer to us. Those are the characterization sites. That's where we go in, dig a pit. We spend hours, we spend a whole day taking those horizons out and getting them down to the laboratory and running characterization work. If you go to Soil Data Explorer, this is what you'll see. You can see the characterization right there. Look at all the Cresbars that have been taken from 1958. I really need a 7-foot stick. I apologize, people. God, why? See, 1958. Okay, 1958 to about 2009. I've got all of those soils that I can look at. I press a stupid button and bingo, I've got all of the physical and the chemical characteristics. I've got mineralogy. I can see how much feldspar is in the sand fraction. I can see what the clay content is. I can see what the clay type is qualitatively, not quantitatively. It's pretty amazing, and it's right at your fingertips, very unlike what I had to do when I was working in the Langland section long ago. Back to the general physiography, we're going to be taking a look at a couple of different aspects here. This is this concept of knowing your geology, okay? And so I want to make a couple points here as we move along. This is the map from that paper in agronomy journal from several years ago, a couple years ago anyway. If you're interested in, if you work in Walsh County, maybe you're on the till plain, maybe you're on the lake plain. If you want to know more about the Edinburgh moraine, then you can actually, there's the Edinburgh moraine. There we go. Okay. There's the Edinburgh moraine, the offshore beach materials, and of course the till plain. If you want to learn more about that, you can read John Bloomley's book on the geology of Walsh County. These are just examples, folks. This is Richland. This is one of my favorites. I was a representative from Eagle Township in '88, but that doesn't matter. These are astounding books, and they're called the Tri-County. They're the county groundwater studies. They're all online now. They're all online. You can find the wells that were measured, hundreds of wells in Richland County. You've got the depths, you've got the characteristics, you've got everything you need to know, and it's all right there at your fingertips at this website right here. The Face of North Dakota by Bloomley is a wonderful guide. If you're new to geology, geomorphology, parent materials, the distributions, the glacial processes, it's astounding. Okay, so let's go back into the geology of the basin and the nature of the soils that we've got right here. Okay. This is from the Manitoba escarpment up here. We can see it, and the top unit's the Odana. That's the Odana shale. Okay, that's the reason that we have to climb that hill as we come out of Grand Forks and head up towards Michigan and Niagara. Okay, because it's a silicious. Excuse my French. It's a silica-laden shale. It's hard silica quartz. Okay, it's a hard shale. And so here you can see multiple units in here. As we go down, we get into the Ordovician and the Silurian. But as you can see, all these things are tipped up to the east. They're tipped up to the east. How much ground do they cover? How much ground do they cover? They've all got different chemistry. They've all got different properties that they would give to a parent material. This is the actual distribution of the amaranth evaporite. Evaporites are soils that are sediment types that you'd be finding in Saudi Arabia and in very, very dry, arid regions. They're loaded with salts. They're loaded with magnesium. They're loaded with chloride. They're loaded with sulfates. Pretty cool. The glacial ice rode across all of that material and brought it down into North Dakota. Okay? So don't ever wonder where the magnesium was. If you're in northern North Dakota, some piece of glacial ice busted up some amaranth and got it into the parent material of your soil. That's pretty cool. Okay, so we can see that distribution. It's not all amaranth evaporite. This is an arkose, and here you can see the striations on this nice rainy day by Sleeping Giant Park in Ontario, and this stuff is as hard as a rock. That literally, it's insanely indurated material. So all you're going to get from glacial abrasion on here is a little bit of quartz and maybe some feldspars. Terribly hard stuff. Very much unlike the amaranth distribution that we just saw. It's all up there in the north. Okay, so we've got all these rock types. But what about the direction that the ice was coming from? Direction that the ice was coming from is it runs the gamut across North Dakota. As you can see, these are ice directions, these are flow directions. There's different birthing processes for the parent materials on your land or on the land that you help offer some knowledge and responsibility for, whether you're a farmer or whether you're an agricultural representative or a scientist. So the fact is, the ice is coming everywhere. Lastly, on this concept, the ice didn't just go down once and go back. It came down again and went back again. It came down again and went back again. This is the Wisconsin. The Wisconsin's the dark stuff here. That's Wisconsin glaciation, 10,000 to 60,000 years ago. If you go into the Illinoisan, that's 130,000 to 300,000 years ago. Bringing all those sediments, all those rocks, changing the landscape, and such and so. And so then you can get it, and that's where the Sangamon, by the way, would have formed during the Illinoisan. And then if you get into Kansas and Nebraskan drift, the light blue, folks, it's 500,000 years old to 750,000 years old. So the parent materials across our landscapes have changed like crazy, and we see that in evaluating the soils of the basin for sure. This is a beautiful image that shows the glacial processes. We were just on a field trip with the Soil Conservation District down at Richland here, standing literally on what I call the snout. And you can look off to the west, and that's the James Lobe going down into South Dakota, and that's where that ice plank went. And then, of course, the other one off to the east is the Des Moines Lobe, all the way down to Des Moines, Iowa. It's an amazing history that we have in our state. It's an astounding history. And geologically, we're blessed in many, many ways. So in terms of time, if we think about time in soils in the basin, if we go off to those shales that are by the Pembina Escarpment, as you can see, you can find Cretaceous aged volcanic ash. That's the white material. That's ash from the Crazy Mountains, maybe the Bighorns, and it fell in those zones. These are black shales. Okay, we've got the highest heavy metal levels anywhere that we've measured in North Dakota up on the Pembina. Okay, and some of that material. These are deep black shales that formed in deep pockets in the ocean in the Cretaceous Sea with organic matter and all the things like uranium, literally, that are associated with it. But we were after, of course, cadmium and zinc, and it was really high. So what kind of fauna did it look like there? If you go to Morton, you can meet Bruce. This is where that parent material, this is what the local animals looked like when that was formed. 85 to 87 million years ago. It's pretty amazing. And now it's right at the surface, and you can dig a hole 4 feet deep and you can find that volcanic ash. It's astounding. It's absolutely astounding. If you go to the Souris Lake Plain, thinking about time, you can see sandhills like this that are a few thousand years old. You can see soils like the Verendrye series here. And if you know what to look for, you can see there's all kinds of buried layers in here, folks. Those are what we call paleosols, just like that Sangamon red one I started with. These are short-lived, tiny little periods of soil development of 50 years, 70 years, 120 years, or whatever, maybe longer, that stabilized those sands, allowed organic matter to accumulate in those sands, and now it's trapped. It's trapped because, of course, it got covered by other dune materials as sands were blowing in that area. So we measured these on the Cheyenne Delta sand dunes, and we've got dates like 3,500 years for our carbon dates. So this is like 3,500 years to 1,000 years. My friend Running measured some. He called them Wimpasols. They were only 890 years old. 890 years to 89 million years. Across the basin, it's pretty astounding. So there's an incredible range in time for the soils and of the parent materials of our basin. Just for kicks, look at the stone line. See the little stone line in here? Look, that particle size is very different than the sands that are above and below it. Okay, marking some sort of a depositional environment there. So if we look at the impact of these shales on soils of the valley, you've got a soil much like this Renshaw or Binford that have all the basins quite rich in shale. If you see that, it's that drab gray color. These shales, of course, were marine, and that's where some of that salt comes from that forms our sodium-affected soils, that forms our saline phases all across the area. So this is what people were cursing about when the wet cycle started in the 90s, and they were starting to see salt seeps in places where they never had seen salt seeps before. The wet cycle in the 90s, as you all well know, was pretty stinking incredible. And I had the good luck to try to sample fine loamy tills across the northern 30 miles from the Canadian line in 1999 with an auger to 5 feet. I took plywood out into the field to bang the auger on because of the mud. Okay, salts were moving everywhere, and a big source of that salt was the shale from this landscape zone. If you look at the till soils in Pierce County on fine loamy till, you can see the upper core cylinder, of course, is dark, very dark, black. It's leached, but that subsoil is loaded with gypsum. Okay, this is 2 feet down, 2.5 feet down. It's loaded with gypsum. Electrical conductivity of 2.2. Soybean problems left, right, and center at a pH, or forgive me, at a pH equal. It's not the pH I'm talking about. It's talking about the salt, but the gypsum levels, of course, are, and that's a sparingly soluble salt. Gypsum is chemically a sparingly soluble salt, and you have much more issues to deal with in terms of salinity than just gypsum in the area. If we think about something like vegetation and climate, as we're at the very eastern edge of the soils of the basin here, we are on the Pembina Escarpment, and this is a particularly poor photograph I took, but I took it for a reason. Everybody in this room can see that there's a gray zone in that surface soil, right? It's not salt, it's not calcium carbonate, okay? This is what that gray zone is. I realized that as I was looking over there, what I was seeing was eroded A horizon, and the E horizon was showing up across that whole field. Okay, and so of course the color differential between the A up here and the E horizon, which is leached, quartz rich, lower pH, calcium, exchange to EC, of course, is much lower than it would be. Let's look at some data for this. The clay content goes from 16% in the E horizon to almost 40% in that horizon below it. So we're talking, folks, about the distance of the thickness of this micro. 16% clay to 40% clay. A high quality soil accepts and retains water. A high quality soil with a 40% clay content at a relatively shallow depth, less than 16 inches, there's 1 foot. Picture a long sustained rain on this kind of landscape on slopes. Water's going to be moving like crazy off on the top of that argillic horizon. That's all there is to it. So it's remarkable. And so again, this is from situations where the original vegetation was forest vegetation. It was cleared by the homesteaders. That deciduous vegetation affected the organic acids, which leached clays, leached organic matter, leached iron, and gave us a completely white layer on top of the argillic horizon. And again, that argillic horizon takes a couple thousand years to form. Going back to the Yellowlands concept. Okay, no surprise, folks, thinking about salinity in a soil like this, where water is the driver for changing the parent material. The salt concentrations are less than 0.8 in the entire profile. You all, many of you all, most of you all would love to have your farm with an EC of less than 8 in the upper 5 feet. Okay, and if you think about the salt concentrations that you've looked at and you've measured, we know they range from soup to nuts across the basin. Okay, they really do. As we think again about the influence of parent materials and groundwater situations, in chemistry, we can look at a Miranda soil from Nelson County here, and there's this E horizon again, a very irregular one on top of another argillic. The salt line is shown right here, very distinctly. If we look at the chemistry, the chemical properties of this, and again, this is why I did that little 2-minute story about the first idea of know your soils and use that database. Bingo, we can take a look at the clay content, okay? in this Miranda soil, and of course it drops in the E horizon, and it increases up to about almost 40% in the argillic. If we look at sodium concentrations, SAR, sodium absorption ratio, older concepts in the 60s and the 70s would have been exchangeable sodium percentage. This is faster to measure, it's quicker, it's cheaper, and the limit is 13 for a sodium affected soil. So look at that Miranda. It's a beautiful name, but it's a pretty appalling soil. My friend Jim Arndt took a picture of a bunch of cattle skeletons on one of the sites that he did on the soil like this. It's kind of an interesting story. This is matrix wheat in northern Pierce. This is what it looks like. The bulk densities in that BT horizon, okay, underneath the E, can be as high as 1.7, 1.8. I've seen bulk densities as high as 2, a little bit over 2 in North Dakota characterization data for sodium affected soils. Folks, an EC of 2 is nuts. You're supposed to have an forgive me, EC, I'm excited to be here. A bulk density of 1.3 is a normal topsoil. A bulk density of 1.6 is root limiting. Your roots will just say, I'm not going down anymore. And we can get 1.8s, 1.9s, and as I said, even higher than that in some cases, but that's the effect, of course, on the spring gradients. Okay, it's a miserable environment in that respect. But let's go to happier stories than that. This was a Friends of Pleistocene trip on the Dalanesker. Look at the sky on that day. I want to show you this picture. Behave yourself. Okay, this is from the top of the esker looking down to the west. These are the till plain soils. These are the beautiful barns and steers. Okay, the whites that you're looking at there, those are your langhais. Those are your Buses and your langhai soils. But notice how dark that is. And so nothing was affected. I didn't change this with kind of photoshopping. They looked that dark that day. So in our prairie soils that we have, thank the Lord for the grasses that grew here, the perennial grasses. That soil organic carbon doesn't dissolve. It can rain from now till doomsday. And that soil organic carbon material will stay in that A horizon for you. Okay, but it takes a long time to make. It takes a long time to make. And so consequently, again, this doesn't hold true for all soils by any means, but in the prairie states like North Dakota, it does. So this is a wonderful thing about our soils. We've been looking at dynamic change on these Barnes profiles. Barnes is a dominant soil across that whole finely tilled plain. This is a Walsh County site that we looked at. I want to show you real quickly what we're looking at in this particular pit. There's your A horizon. There's a nice slice of the A horizon. It's got granular structure. It's dark. It's really a lovely little soil. But here, now pay attention and look at this, folks. That's the BW horizon. That's the horizon below the A. Look at that color. And there's my knife to show you what that brown, rich color is. That's a leached horizon. Water's moved through that and has moved out all of the soluble materials, and you're left with a very productive BW horizon or a cambic horizon with beautiful structure. And of course, below that, we would have the normal calcic horizon, that white horizon. This is a beautiful soil. Okay, last point on this idea of the Barnes. The dates, here's dates that were published in 1979 in Soil Taxonomy, carbon dates for the Moloch epipedon. That's the mollisols. Those are our prairie chernozems, our black earths. Notice the first one is Cavalier County, North Dakota. And look at the date of the carbon 14 data for that. The average date of the carbon in that A horizon was 350 years. And of course, it ranges across the area. Some are as low as 210, some above 400, 440. That Moloch epipedon, which is the heartbeat of the productivity of the soil, of these prairie soils, takes a long time to make. Takes a long time to accumulate. Takes a long time to come to equilibrium or quasi-equilibrium in the soil system. Okay, so the takeaway for me is that soil carbon is regenerated one generation at a time. not by a 5-year farm program. Okay, now that's just me. If we want to argue about that, we can argue about that later, but that's what I say from digging thousands of holes in North Dakota. Oh, there we go. Okay, so here's a Barnes, here's a beautiful Barnes image from the 30s. William Johnson did a WPA project in the 30s, and he took pictures all across central and northern North Dakota. And here you can see a Barnes, and look at where the 1 foot mark is, and look at where the calcium carbonate comes in, way down here, well below a foot, well below 1 foot. That's that leached prairie soil. Soluble materials, including limestone, have been mobilized and moved, and that carbonate has been moved down, the calcium has been moved down, and the calcium carbonate accumulates at depth at the desiccation front when the water gives up everything that it's got. This is a wonderful treasure, these photographs that we have. Is it working? Behave yourself. I must have run out of battery. Could you push next if you can? This is where Barnes is found. This is where Barnes is found, folks. This is such an important soil. Productivity index for spring wheat of 85. Top is 100, but that's going to be in a soil like Overley, not Barnes. Anyway, 4.3 million acres of it in our region. This is an important soil. Okay. I want to share a couple ideas of some of the micromorphology work that I've done. And it starts down in those many townships between Western Cass and Eastern Stutzman County. We did 2 townships north and south of I-94, and Meyer took 180 some samples, and I did micromorphology in about 6 of them. So what are we talking about here? One that I probably got to move along. Additionally, besides the soil health area, I did reference sites, thanks to Wade Bott giving me some good money for additional work. These are native sites. These are native sites that have never been plowed. And we'll take a look up here when I finish on reference site 2. Okay, I'm sorry. Okay, so here's the Devil's Lake area. That's the Barnes reference site over there. Okay, I'll show you that at the end. That's a wonderful take-home message for everybody here in this room. Okay, we're going to look at just a couple ideas here. I don't have time to share this with you, but once I was scared to devil to give a faculty seminar, and I'm looking at this book on my table in the dining room, and I'm looking down and I'm going, God, the cover of that looks really familiar. And I went, hell's bells, that's Egg Creek. I've mapped soils in McHenry County. And the picture of this was on the cover of this wonderful SSSA special publication. How cool is that? Okay, when we looked at the soils in the basin that were going to be irrigated, we had to look at the fine loamy tills, because as you saw, that was that great brown area. Well, they're all mapped as loams. The ones that we're looking at here, these sites 2A, 6, and site 7, they were all mapped as loams. Look at those pH. Look at the clay content, folks. Where does clay loam begin? On the textural triangle. 2 tenors, come on. It begins at 27%. How many of those numbers are greater than 27% clay? Again, it's going to affect water movement. It's going to affect water retention. It's certainly going to affect ease of water movement through the soil if you're talking about an irrigation system, right? So you have to play that game. Clay is funny. You want enough of it to retain water, but you don't want so much of it that it'll allow water to run off or not move in. This is the Candu Lake Plain. This was site 6. Okay, this was mapped as a silty lake plain. Okay, a silty lake plain on that map that I showed you earlier. When Kyle and I were out poking holes all through this region, and we poked lots of holes. Right there, we were augering down. We got to around 50 inches, and we're texturing this, and we're going, what in the world? We took it back, and Keith Jacobson, who was a phenomenal analyst, ran the clay content, and it was 78.9% clay. Folks, that's an insane clay content. That's a stinking insane clay content. We don't have that in the valley. We don't have that in the valley, only on the very fine soils in the valley, like North Coast, we get that. So consequently, in terms of irrigation, that's going to set up a first water table like crazy at 50 inches. Okay, everybody with me? It's serious business. The other thing that I want to share quickly is that when we look at, this is the big point, these were what we call ECA zones, and there were about 20 sites in here that were randomly associated to measure what that effective irrigation would be over the few years of the test project to see whether we would kick up salinity a little bit. Well, this is site 2 and this is what it looked like going out and sampling. You can see the flag pictures there. Okay, now look at site 2, folks. That increased 0.8, and to me, 0.8 is just a 1. And anybody in here that farms does not want to see the EC of a particular chunk of ground on their farm go up a whole unit of EC. So that was the result of the irrigation over several years. Okay, quickly. That was the result of irrigation over several years. And of course, the other site didn't see that. The other ECA site that was outside the pivot did not show that, but this one did. Why did it do it? Why did it do it? It did it right there's the A station A2, and there's the site that we're talking about right there, 702. It's not the irrigation water. It's not the irrigation water. Site 7 pumped the third highest amount of all the 10 sites, and the irrigation water was 1.2 decisiemens per liter. Okay, relatively low. And so consequently, that was interesting. So the water was good, but look at the subsoil chemistry. Look at that subsoil chemistry at site A2. That's the pink one. That's the pink one. There was a hydraulic connection between the irrigation water and the underlying soil chemistry that allowed that water through capillary rise when that corn was growing like crazy to accumulate that salinity. So that's why the characterization data is helpful to us, and being able to tap into it in soil lesson number 1 from this talk is really pretty key. This was a sandy soil that was also part of that site, and that sandy soil, of course, was clean as a bell all the way down. Okay, cautionary tale, micromorphology. I have to do this very quickly, and I apologize about that. You can take pieces of soil, you can basically freeze them in a resin, and you can slice them on a tiling saw, and you can make a thin section. That's a thin section right there. When I look at dynamic soil change, this is Western Walsh County, as I'm joking about Alan Dalton's, who some of you know, he's pointing out the bloody obvious on this particular field. This is what the soil looked like. This is what the soil looked like. Those soybeans were nice and honey green. And he said, hey, that looks okay. Well, that's what it looks like underneath the soybeans. And the calcium carbonate content in the A horizon was 1.4%, and it was 14 in the PW horizon right there. It's 14% by weight. Calcium carbonate, pH is going to be 8.2. Soybeans like a pH 8.2? Oh, they surely do not. Okay? This is a problem. We're being able to see this sort of thing in the micromorphology when we look at it, and we can see these calcic colors right in here. Those are the calcic colors, and we can measure those with fancy image analysis software, and we can actually calculate how much is there. And here's just a quick example of one of Meyer's sites where that counting, which is shown up here in a general sense, said that the calcic load visually was about 10%. When Meyer measured that in the laboratory, the A horizon of this particular soil was 6.4 and the B was 15.8. That average is 11. I'd say we've done a pretty good job with micromorphology to show that we're looking at some serious problems in terms of potential on these soils as a result of erosion. Now, we look at the native barns over at that reference site, okay? There's the knife marking the bottom of the A horizon, and that's what the A horizon looks like. Folks, you would love to have a soil like this. Every single one of you would love to have all of the soils on your property look like this. Okay, I gotta go. This is beautiful. On that particular site, after hundreds of thin sections, I saw fine root hairs coming out of a plant root. I've never seen them before on all of the ones I've looked at. And I'm the only person that's made thin sections for soil in the state's history for the experiment station. It's an astounding thing. And so it marks soil quality. We've got to watch what we're doing. Okay, we've got to watch what we're doing. I hope that the travel log has been meaningful in some sense. Thanks for your time.